Namaste and welcome to yet another lecture on linear algebra through geometry. In the previous lecture we saw the idea of LU decomposition and we also looked at the idea of solving system of equations in let us say 3 variables and 3 equations and 3 variables. Then we looked at the idea of what is it to say we have unique solution, what is it to say we have infinitely many solution, and what is it to say we have no solution. We also looked at the idea of homogeneous system of equations. And what are we going to do in this class? We looked at LU decomposition till LU decomposition in the last lecture. In today's lecture what we are going to do is we are going to look at the idea of least squared solution. Basically we are going to look at a system of equations where you do not have a solution. Suppose you are given a system of equation, let us say Ax equal to b, and the question is solve for x. Suppose if you find that there is no x such that Ax is equal to b, in that case what is it that we do. So this was the question that we had. Probably even in 2D we faced this problem where we looked at let us say this example. In 2D we took this example. Suppose if I take this 2x1 plus x2 is equal to 3 and 2x1 plus x2 is equal to 4. So let me write this. So we are going to look at least squared solutions. Just the general idea of this least squared solutions and how do we go about getting the approximate solution. And what are we going to do is we will generalize this at a later point of time, but then we look at it from an n dimensional vector space at a later point of time. But what we are going to do is we are just going to get a rough idea about how do we go about solving a system of equations for which there exists no solution. For example, you look at this, the pair of equations that we have given, the left hand side seems to be the same whereas the right hand side seems to be two different measurements, and this clearly says that there can be only one of the equations can be true at a particular time. You cannot have the same thing which says like 2 quantities of x1 plus 1 quantity of x2 at one point gives me 3, and the same 2 quantities of x1 plus 1 quantity of x2 at another time gives me 4. So we say that there is no solution that exists here, no solution exists, right. Similarly let us take another example here where we have in 3D. Let us look at in 3D. Of course what we are going to do is we are just looking at we are going to take up this, let us say let us take another example. So example, I have x1 plus x2 is equal to 2, x1 minus x2 is equal to 0, and 2x1 plus x2 is equal to 4. Assume that this is the equation of the line L1 and this is the equation of line L2 and this is the equation of line L3. Now from here we can actually look at we can get the coefficient matrix A, which is of the form 1 1 2. We are going to have 1 minus 1 1, this is A, and I am going to have x vector which is going to be this x1 x2, and I am going to have my b vector which is basically given by 2 0 4. Now what is interesting here is the second equation, let us say L2, it clearly says that x1 is equal to x2 is the solution, and if you substitute x1 is equal to x2 there, that means x1 is equal to 1 and x2 is equal to 1 in the first equation we get 2. That means the first two equations get they are satisfied with the value x1 is equal to 1 and x2 is equal to 1. However, if you substitute x1 is equal to 1 and x2 is equal to 1 in the third equation, we find that it does not satisfy the equation. Basically the left hand side does not equal to the right hand side. So in which case there is no solution that exists. We find that no solution exists. It can even be seen very easily in terms of geometry when we look at let us say the system of equations as let us say straight lines. Let us just look at this 1 2 3 4 5 6 7 1 2 3 4 5. The first equation x1 is equal to x2 basically says that this is the line that we are going to get, let us say 1 2 3 4 5 6 7 1 2 3 4, this is 0, this is -1, let us say -1 -2 and so on. So, the first line that we see, is basically if you put x1 is equal to 0, x2 is 2, and if you put x2 is equal to 0, x1 is 2. So, we are going to get a line which is going to be like this. Second equation, we already know the line that we are going to get is basically x1 is equal to x2 line. So, this basically passes through this and intersects. So, this is basically the point of intersection which is 1 comma 1. The third equation we have 2x1 plus x2 is equal to 4. If you put x1 is equal to 0, we get x2 is equal to we have x2 is equal to 4. If you put x2 is equal to 0, we have x1 is equal to 2, and we see that these two lines, they basically intersect at some other point. So, what we see is the three lines that we have, the corresponding equations which are given here, are basically lines where at any point of time you have two lines to intersect at one point. All the three lines do not intersect at one point. There are, for example, if you look at this, L1 and L2 intersect at this point, L1 and I mean this L3 and L2 intersect at this point, then we have L1 I mean L2 and L3 intersect at this point, and we have L1 and L3 intersecting at this point. Therefore, there exists no solution. Now, if we see the vector way of this, if you look at it as linear combination of vectors, so we can write this as, so in the vector perspective we have the following. In the vector perspective, or the column picture that we actually call, in the column picture we have the following. What do we have? We have x1 into 1 1 2 plus x2 into 1 minus 1 1 is equal to 2 0 4, and what we see is we figured out that you cannot find a scalar x1 and x2 such that the right hand side vector 2 0 4 can be expressed as a linear combination of these two vectors, and this essentially boils down to the geometry we had already seen before, where I have, let us say this is my x1 axis, I mean I have x1 x2 x3 axis, let us say x1 x2 x3 axis. Now, what do we have here? I have a vector which is, let us say this is A1 corresponding to the first column of the matrix, and let us say I have this vector A2 corresponding to the second column of the matrix. My B vector is going to be somewhere here. In this case, we see that B can never be expressed as a linear combination of the two vectors A1 and A2, because A1 and A2 are basically, they form a plane, and this vector B, the A1 and A2 vector, determine a plane, and then the B vector is not in the plane. Therefore, we cannot do this, but not all is lost. The reason is we already know that if we project this B vector onto the plane, and that projection of B onto the plane which is determined by the vector A1 and A2 is going to be the best approximate or the best representative of the vector B in the plane which is determined by A1 A2. This is something which we saw already. What is that? We say that if you project this orthogonally, if you do an orthogonal projection onto the plane, let me call this as let us say B star. So, the B star is going to be a point in the plane which is, so B star is, the vector B star is in the plane determined by let us say in the plane, I will put this as pi A1 A2, because those two fellows determine the plane. So, we say that it is in the plane. The moment B star is in the plane, I can express B star as a linear combination of the two vectors A1 and A2, and this guy that is there, this is basically my B perpendicular, which is the error, right. And we know that B star, we already have seen, is basically if you project a vector onto another vector, we know that the projection is going to be the best representative of the vector along the direction of the other vector. So, that is something which we have seen. So, that is exactly the principle that we want to do. The moment I have this B star, I can always find out. So, once we know, once we get B star, which is the projection of B onto the plane let us say pi a1 a2 to say that it is basically determined by these two linearly independent vectors pi a1 a2, we can find. So, let us say scalars x1 star and x2 star such that x1 star into the first column of the matrix, let us say A1 plus x2 star, we will just check what it is, okay, just a minute, okay, such that, okay, we can get we can express B star as linear combination of A1 and A2. This is what we have, right. Okay. So, what is it that we do here? Let's figure out. So, let's write this. So, we know that the vector B is equal to the vector B star plus the vector B perpendicular, which we saw in the previous case here. So, this is B star which is along here and this is B. So, basically what have I done? I have basically decomposed this vector B into two orthogonal components, namely B star and B perpendicular. That is what we have here. So, what do we say? We say that B star is closest to B in the plane pi, let us say A1 A2, where A1 A2 is basically the columns of this matrix A, and B perpendicular is orthogonal to the plane to pi A1 A2. Now, from that what do we understand? We say that A1, the vector A1 transpose B perpendicular is equal to 0, because they are B perpendicular is orthogonal to the plane, therefore, it will be orthogonal to the two vectors A1 and A2, and A2 star, I mean A2 transpose B perpendicular is also equal to 0, where A1 and A2 are, let us say, the columns of A, right. This is what we have, which means essentially I say that it is A transpose, it is A1 transpose A2 transpose B perpendicular. So, I am going to say A transpose B perpendicular is equal to 0, which, and we know that B perpendicular is nothing but the vector B minus the vector B star. So, what are we going to do? We are going to say that A transpose into B minus B star is going to be 0, but since B star is going to be there in the plane, I can write that as A x star. So, I am going to write this as, okay, let us write this, since B star is in the plane pi A1 A2, B star can be written as A x star, where x star is equal to, in our case we have this x1 x2, in our case it is a 2 component vector. So, we have this. So, what are we going to do? We are going to write this as, so we have A transpose into the vector B minus A x star is equal to 0, which means I am going to have A transpose B minus A transpose A x star is equal to 0, which implies A transpose A x star is equal to A transpose B. Now what have we done basically, if you look at it very carefully, initially we had Ax equal to B. Now what did we do? We ended up looking at, instead of solving for Ax equal to B, we now solve A transpose Ax star is equal to A transpose B. This is what we are trying to solve, and so that is what we are going to do. So look at, we now solve A transpose A x star is equal to A transpose B. We are not going to solve for Ax equal to B, instead we are going to solve for A transpose A x star is equal to A transpose B. Now if the solution exists, then we are going to say that the squared difference between the vector B and the vector B star, which is basically my component along the plane, the squared distance is going to be minimum, and that value of x star which gives this minimum is basically what we call as our least square solution. That is what we are going to see. So let us look at what it is, right. So let us see that. So we have, essentially we see that A transpose A is a square matrix and symmetric, too, right. This is what we have. So what are we going to say? This is there, suppose. So the solution x star, let me call this as, let us say, equation 1. So the solution to 1, or the solution x star to 1 when exists, when it has 1, that means if it has a solution, is the one that minimizes the error. What is the error? That is basically the perpendicular component that we have, which is nothing but A x star minus B vector the whole square, and x star is basically the least squared solution. And in the example that we took, basically in our example, we have A transpose B is equal to 1 1 2 1 minus 1 4 1 minus 1 1 into 2 0 4. This is A transpose B, which is equal to 2 plus 0 plus 8, which is 10, and then 2 plus 0 plus 4, which is 6. So A transpose B is 6. We have A transpose A is nothing but A transpose A is 1 1 2 1 minus 1 1 into 1 1 2 1 minus 1 1 which is nothing but 4 2 2 3. If we see, this is 1 plus 1 plus, so it is basically okay 1 plus 1 2 plus 4 6, sorry. So we have so it is basically 1 plus 1 2 plus 4 6, then we have 1 minus 1 0 plus 2. So you have 6 2, it is basically again 1 minus 1 0 plus this is 2, then we have 1 plus 1 plus 1 3. So we have 6 2 2 3. Now all we can do is we can find out x star, which is nothing but A transpose A the whole inverse into A transpose B, and we know the inverse of this 2 by 2 matrix. So the inverse of that is basically 1 by determinant of A 1 by determinant of A transpose A into adjoint of A transpose A into A transpose B. So, we get 1 by determinant of A transpose A is 18 minus 4, which is 14, into adjoint of A, we already know it is basically our swapping of this diagonal elements and then changing the sign of the off diagonal elements, and we have this which was basically 10 and 6, which is nothing but 30 minus 12, 18 by 14, and we have minus 20 plus 36, which is 16 by 14. So, my x star is going to be this. Okay. So, this is about the least squared solution. So, what it says is, in case where we do not have a solution, Ax equal to b does not have a solution, we can look at what is called as least squared solution, which is basically going to minimize the squared error between the given right hand side b and the actual b star that we get, which is basically the projection of b onto the geometry, which is like basically the projection of b onto the geometry which is formed by our the vectors of the column vectors of the matrix A. Is that okay? So, that is what it is. Now, having seen this, where do we go ahead? Having seen this, what do we do? We are going to look at the idea of, let us say, inner products. We are going to look at the idea of inner product and the idea of what we call as and the algorithm, which is basically the Gram-Schmidt orthonormalization, Gram-Schmidt orthonormalization followed by QR decomposition. Then QR decomposition. This is what we are going to look at now. Now, we already have seen the notion of inner product from a different perspective, where we actually looked at the dot product. We have actually we know the definition of dot product, we know the idea of dot product of two vectors. So, the what we can say is inner product is basically a generalization of dot product. So, what we do is the inner product of two vectors. So, given two vectors, the only thing is the two vectors must have the same number of components. So, given two vectors u and v, we define the inner product as of u comma v as u comma v is equal to v transpose u, which is the same as u transpose v, which is the same as let us say this, because we already know v transpose u is v1 u1 plus v2 u2 plus v3 u3 etc. So, therefore, that is the same as u1 v1 plus u2 v2 plus u3 v3 etc. So, we are going to have the inner product to be defined as. So, there are some of these interesting properties of this inner product. So, we are going to look one by one. We are going to say for any scalar k, we are going to have suppose you scale a vector u and then you try to find out the inner product of that with v. This is the same as scaling the vector v, this is the same as scaling the vector v and finding the inner product with u, which is the same as scaling the inner product of u comma v, which we already know. So, because u dot v is u1 v1 plus u2 v2. So, we have if k u1 and k u2 you have. So, we have k u1 v1 plus k u2 v2. So, that is going to make it k times u1 v1 plus u2 v2, that means k times the inner product of u comma v. So, the second property that we are going to have is for three vectors, for any three vectors u, v and w, we have the inner product of u plus v with w is the same as the inner product of u with w plus the inner product of v with w. And the most important property is this: for all vectors, or let us say for any vector v, any vector v, v, the inner product of v with itself is always greater than or equal to 0. V, the inner product of v with b is equal to 0 if and only if v is the 0 vector. V is the 0 vector. Having defined the inner product as the I mean v transpose u and u transpose v, all these properties can be easily proved. So, yeah, so we can take I mean I will leave that as an exercise, so that you can prove this and then check if these properties are fine. Now, why do we need this? We are going to look at I mean in fact the idea of length comes from the length of a vector comes from the definition of inner product in a vector space. We will see that the inner product vector space and stuff when we do vector spaces. Okay. Now, what we are going to do is we are going to get on to a question given, let us say 3 vectors u, v and w, u, v and w, let us say linearly independent. We already have seen the definition of linear dependence, independence and stuff. So, let us look at linearly independent. Our question is like, can we find 3 vectors, say phi 1, phi 2 and phi 3 orthogonal to each other from u, v and w. So, given these 3 vectors, now our lookout is basically for finding out 3 vectors phi 1, phi 2, phi 3 which are orthogonal to each other. U, v and w are linearly independent vectors. From u, v and w I want to generate 3 vectors phi 1, phi 2, phi 3 which are basically orthogonal to each other. Can we do it? This is also something interesting which we have done before, it is not that we did not do it. Recall that if I have, let us say I have a vector which is a here, and let me say I have another vector b which is along this direction. If I project b onto a, this is basically let us say the projection of b which is given by t times a, which we have done. If I project b onto a and subtract the projection, then I am going to get b perpendicular, and b perpendicular is orthogonal to a. That means from b now I have generated another vector b from a and b, I have generated 2 vectors, namely a and b perpendicular which are orthogonal to each other. So, how did I generate? I basically got b perpendicular to be b minus projection of b onto a. B minus projection of b onto a gave me a b perpendicular, and what is the interesting thing about b perpendicular? B perpendicular dot a is basically 0. That means b perpendicular is orthogonal to the vector a. Is that clear? Now, for 2 vectors we are able to find out another pair of vectors, namely a and b perpendicular which are orthogonal to each other. Now, can we find out for 3 vectors, is it possible to find 3 orthogonal vectors, and that is exactly where we get into idea of Gram-Schmidt procedure for finding out this. The procedure is pretty simple. What is that? If you have a set of vectors, linearly independent vectors, take one vector to be the first vector to be the reference vector, and then what do? You project the second vector onto the first reference vector, remove the projection. So, you are going to get 2 vectors which are orthogonal to each other. Now, what you do, if you want to get the third vector which is orthogonal to these 2 vectors, take the third vector, project the third vector onto these two already orthogonal vectors, subtract these projections, you are going to get a third vector which is orthogonal to all the three, I mean the other two vectors. So, we in essence we are going to get 3 orthogonal vectors. So, what are we going to do? So, we are going to do this. So, I am going to look at phi 1 vector, which I will take this as to be the vector u itself. What I do, phi 2 vector, in order to find the phi 2 vector, I will take v vector minus projection of v onto the direction of phi 1, right. Basically I will do this, I will project the vector v onto the direction of in the direction of phi 1 and remove that projection. So, what does that mean? It is going to be v minus v dot phi 1 by phi 1 dot phi 1 in the direction of phi 1. Similarly, now I want to get phi 3, which is another vector which is basically obtained by taking w, subtract w, I mean subtract the projection of w in the direction of phi 1, which is this, and also project the w vector onto phi 2 direction, subtract that projection also. Now, what we see is, we see that phi 1 dot phi 2 is 0, we will see that phi 1 dot phi 3 is also 0 and phi 1 phi 2 dot phi 3 is also 0. Why is phi 1 dot phi 2 0? What we have done? We have projected v vector onto the direction of phi 1, that means it was something like this. So, let us take 3 vectors now. So, what have we done? Let us assume that I have this vector which is basically my u vector, and let us say I had this vector which was v, I had this vector v, and let us say I had another vector which is w. Let us take this is the vector w. Now, what did we do? We first projected v onto u and subtracted the projection, that means this is the component that we get. So, we see that this v perpendicular component and u are orthogonal to each other. Then what I do? I basically project this w onto this direction, which was basically the phi 1 direction, and then onto the vector v perpendicular. So, we are going to get another vector which, and then subtract those projections, we are going to get this vector phi 3, which is going to be orthogonal to all these 3 vectors. Is that clear? So, this process is typically repeated, and this is what we call as Gram-Schmidt orthogonalization process. And of course, the interesting thing is the vectors phi 1, phi 2, phi 3, they are not unit vectors. So, you just try to normalize it by dividing it the vectors by the length. So, you get your orthonormal vectors, that means vectors which are orthogonal to each other and the vectors which are of unit length. Is that clear? So, that is basically my Gram-Schmidt orthonormalization. So, I will say now E 1 is equal to phi 1 divided by the length of phi 1, E 2 is another vector which is basically phi 2 divided by this, and E 3 is basically phi 3 vector divided by the length of phi 3. So, now what we see is E 1, E 2, E 3, all of them are of unit length and all these 3 are orthogonal to each other. So, this is what is basically our Gram-Schmidt orthonormalization process. Okay. Now, why do we need this Gram-Schmidt orthonormalization process? We basically end up getting orthogonal vectors, and in fact, it is very interesting to note that from this, suppose if we have this, suppose we have a matrix A, we had A to be the matrix whose columns were these vectors u, v and w. Suppose we had this matrix which was u, v and w, this is what we had. Now, we can express this A matrix and from the given what you call, from the Gram-Schmidt procedure, we can get u, the vector u is basically, let us say it is phi 1 into E 1, phi 2 into E 2 is the vector, phi 2 into okay, let us do that. Okay. So, the vector u in this case is nothing but I will write this as it is basically okay. Anyway, we will do this in detail of course, in when we do the inner product vector spaces, where we will be able to express this matrix A as we can express this as a product of two matrices, namely Q and R, where Q is the orthogonal matrix, or in fact matrix with columns which are orthogonal to each other, and each the column metric measuring unit length, and R matrix to be the upper triangular matrix. So, that is what we are going to have it as QR. So, let us basically do that quickly. So, I have my u vector from in the first case was phi 1, u vector was the vector phi 1, which is nothing but E1 vector, it is basically modulus of phi 1 vector into E1. The vector V was basically phi 2 vector, this was basically phi 2 vector plus projection of V vector onto the direction of phi 1. This is what we had, which is nothing but phi 2 vector was basically the norm of phi 2 into E2 vector, this is what we had, plus projection of this, which is nothing but V dot phi 1. So, what we had V dot phi 1 divided by phi 1 dot phi 1 in the direction of phi 1, phi 1 is nothing but this phi 1 into E1 vector, this is what we had. Similarly, we have W vector to be phi 3 vector, phi 3 vector is nothing but phi 3 vector plus projection of W onto phi 1 direction plus projection of W onto phi 2 direction, this is what we had. So, what are we going to have? What is phi 3 vector? Sorry. So, we are going to have W vector to be phi 3 vector, phi 3 vector is basically the norm of phi 3 into the E3 vector plus projection of W onto phi 1, projection of W onto phi 1 is nothing but W 1 dot phi 1 divided by phi 1 dot phi 1, and basically we looked at the unit vector. So, this is going to be along the direction of phi 1, along the direction of phi 1 is phi 1 vector into E1 vector plus W dot phi 2 divided by phi 2 dot phi 2 in the direction of this phi 2 in the direction of E2 vector, this is what we had. So, it is very easy to see that phi 1 dot phi 1 and this gets knocked out. So, let us look at this. So, basically what are we going to get? We are going to see that we can write A is equal to, I will write this as the first vector E1, E2, E3, these 3 vectors. I can write it because I had U and V and W. So, let me express all these things together. So, A was this matrix U, V and W. So, I am going to write this as the first column is vector length of phi 1 into E1, then the second vector V was basically phi 2 vector into E2 vector plus V dot phi 1 divided by phi 1 dot phi 1 in the direction of, and the third vector was this whatever W vector here. So, this entire thing comes in, sits here. Now, what we can see is we can actually split this as say E1 vector, E2 vector and E3 vector. I will basically pull out these, and because E1, E2, E3 they all get scaled by some value. So, what do I have here? This is basically I have this phi 1. So, this is basically the length of phi 1 0 0, then we are going to have E 2 is basically multiplied by length of phi 2, and on top of it you have this multiplying E 1. So, this is nothing but V dot phi 1 divided by phi 1 dot phi 1 into this 0. Then what do we have here? We have the same thing here, W dot phi 1 divided by phi 1 dot phi 1 into phi 1, vector length W dot phi 2 divided by phi 2 dot phi 2 in the direction of phi 2, and then we have this. So, this matrix is an orthogonal matrix, we call this as Q, and this is an upper triangular matrix R. So, we have what is known as Q A is equal to Q R, that is a Q R. So, basically this is what we call as Q R factorization, that means product of orthogonal matrix and an upper triangular matrix. Right. So, what is interesting about this orthogonal matrix? Let us just write the properties of it. So, orthogonal matrix Q has the property that columns of Q are all unit vectors that means their length is 1. The column vectors of the columns of Q are orthogonal to each other and more interesting property is that if you have such a matrix, the inverse Q inverse is equal to Q transpose. So, that is what we call as an orthogonal matrix. So, basically we have seen two types of decomposition right now, namely the LU decomposition, and we have also looked at QR decomposition. The other topic, eigenvalue eigenvectors, we have already seen it with respect to reflection and other matrix. The idea is already carried out in terms of finding the characteristic equation and then solving the system of equations A minus lambda I times x is equal to 0, you get the eigenvalues and eigenvectors. Now, so this overall unit, if you actually see, if you look at this entire module, we basically started off looking at solving systems of equation 3D in 3D, that means 3 equations and 3 unknowns. We basically looked at the column perspective of the system of equations to figure out when do we have unique solution, when do we have infinitely many solution, and when do we have no solution. And we also looked at the homogeneous system of equation. We basically looked at following the homogeneous system of equations, and we also looked at this notion of Gaussian elimination and stuff. Then we followed it up with finding the least squared solution, which is basically the best approximate solution that you get in case where you do not have a solution. And then we looked at the idea of orthonormalization, Gram-Schmidt process, where we typically got a set of orthogonal vectors from a set of linearly independent vectors. And we also these set of this entire procedure of orthogonalization or orthonormalization, the Gram-Schmidt procedure helped us also to decompose a given matrix A in terms of product of an orthogonal matrix and an upper triangular matrix R. So, we had A is equal to QR. In fact, this is very interesting because it also helps us to solve system of equation in case we want to find out A inverse. If A is a square matrix and inverse is all, you can get inverse, you can actually get the inverse of the matrix through QR decomposition, which is basically easier to get. So, this is what we have seen in this module. So, where do we go from here? So, ultimately what we have seen is we have looked at what happens with a set of vectors in 2 dimension, we have looked at what happens with a set of vectors in 3 dimension. Now, we just want to generalize this to any n dimension, and that is exactly where we are going to define or we are going to look at the idea of vector spaces. We are going to look at the idea of what is it to look, what is it basically that we are looking at in terms of vector spaces, what do we have what is it that we call as subspaces of a vector space. Then we are going to look at the idea of basis for a vector space and dimension and so on. So, that will form our next module. In the next module we will generalize all these ideas that we have studied in terms of vectors. We are going to get into the generalizations, we are going to look at the idea of vector spaces in the next module. Thank you.